Hello, statistics fans, and welcome to Math 215. Our section today is section 1.3, which is Introduction to Experimental Design. Sometimes this is referred to as design of experiments, and it's actually an extremely important topic in statistics and in research generally. So this is a first year stats class, so we are going to cover this topic in just one section. But in reality, if you go into research or if you minor or major in statistics, you take an entire class called Design of Experiments. So there's a lot of information. It's a really important topic, but we're just going to skim the surface so we'll get an introduction to it. So there's some basic guidelines for planning a statistical study. And these I just copied out of the book here. It's on page 22 of the book. And any stats book will have something very similar to this, just some general things to keep in mind. A lot of these things we'll talk about as we go on here, so I'm not going to sit here and read these to you, but you should just pause a minute and read through these. So to get started here, let's see, sometimes the goal of our study is to understand the cause and effect relationships between two or more variables. Such studies can be complicated by lurking variables or confounding variables. And we'll find out that this cause and effect relationship they're talking about, cause and effect relationship, these are extremely difficult to prove or to lock down so that you are very confident that there is a cause and effect and not just a correlation. So not an easy thing to show. A lot of times it's because of these lurking or confounding variables. So a lurking variable is one for which no data have been collected, but that nevertheless has an influence on other variables in the study. So the example they have is a research scientist studies the effects of diet and exercise on a person's blood pressure. Lurking variables that also affect blood pressure are whether a person smokes, and stress levels. So if you publish the results of your study and you have not controlled for these two things and many other things, then your paper is going to be met with a lot of criticism because whether a person smokes makes a difference. So if you're going to design this study, you're going to want either everyone to smoke or no one to smoke, because you don't want later somebody to say, well, you show there's a result here, but maybe it's just because there were smokers here, right? So we have to control for these things. Stress levels would be important. Some people have very stressful jobs or stressful homes, and that's something that you're going to have to control for, so that you basically want everybody to be as close as possible in all the measurable ways, and then you just want to change one thing, right? So studying the effects of diet and exercise. So if we're just going to look at diet and exercise, we want everything else to be the same. Okay, so these are lurking variables. Lurking variables, sometimes you're not even aware of them. So sometimes you could set up this study and you're done, you run through your entire study, and then when it's published, someone mentions, or even one of the people providing the peer review may say, did you control for such and such variable? And maybe you didn't even think of it. So lurking variables are sometimes not even measured or considered. Two variables are confounded when the effects of one cannot be distinguished from the effects of the other. So as an example, there appears to be a relationship between ice cream consumption guess I needed a longer line there, huh? And number of drowning deaths. So there's a very strong correlation between ice cream consumption and drowning deaths. So that doesn't really mean that eating ice cream causes you to drown, though, right? So, and nobody, in this case, it's really obvious, but in a lot of cases, it's not. So we'll see later on in chapter 9 that we have to be careful between confusing correlation with causation. But instead of thinking that eating ice cream causes you to drown, the more likely explanation is the relationship between ice cream consumption and drowning is spurious, and that there's a third confounding variable. The season that also influences drowning. So during the summer, of course, you have warmer temperatures, and in the summertime, people tend to not only eat ice cream more, but also swim more. And of course, there are more boating accidents also during this time, and nobody associates that with eating ice cream. So now we have to talk about how do we get this data. And there are many ways to produce data. The first one we look at is the census. So if we use measurements or observations from the entire population, we have a census. This is rarely done. As you know, we have, the United States has a census every 10 years, and this is in fact a census year. So many of you, I'm sure, have already filled out a form. Here's some information about the census. It happens every 10 years since 1790. And one of the main reasons we have it is to figure out how many seats each state receives in the U.S. House of Representatives. But federal and state governments rely on census data to budget for social programs, and demographic figures are useful for planners when planning hospitals, housing developments, and even looking at information for schools or whether or not your town needs a new strip mall. And let's see, what else do we have here? Well, here's something kind of interesting. The primary goal of the original 1790 census was to provide information on men eligible for the military. That first census project cost $45,000. And the latest census from 2020 is projected to cost $15.6 billion, which comes out to be about $100 per household. But one thing you may have noticed, this is the first time this has happened, in the 2020 census could be completed online. That's the first time. So most households received a mailed invitation around March. And the first people who were able to participate in the census is always these rural Alaskan villages, and they have to get counted first because when it thaws in the spring, it makes it almost impossible to move around up there. Also, law requires each batch of census forms to remain private for 72 years, and these things are really private. The Census Bureau cannot share the census answers with any other government agencies. So the complete 1950 census records will be released in April of 2022. But this way of producing and gathering data is rarely used because it's extremely expensive, as you can imagine. So it is one way to get data, but it is not done very often. So if we use measurements or observations from only part of the population, we have a sample. And so recall sampling techniques from the last section. talked about ways of sampling in section 1.2. And the note is, in this book, the author mentions this, but in this book, simple random samples are used. So when data are given, we can assume it comes from a simple random sample. Okay, so we've got a census, we've got sampling. Another thing that can happen is data may be produced through computer simulation. This is often used when a procedure would be costly or dangerous. So as an example, if you wanted to consider the effects of nuclear radiation, well, there were experiments with nuclear radiation starting in the 1940s, but now we have very good computer models. So, we don't really, we don't set off nuclear bombs anymore, at least not in the United States, right? We've got really good computer models, so we can predict pretty accurately what's going to happen, because we know the effects of we understand the physics, and we have experimented in the past, so our models are really good here. Also, something like wind shear on airplane wings. We don't have to have the test pilot do crazy things. We don't even really need to use a wind tunnel as much anymore, because the physics are understood so that our computer models are pretty good. Wind shear is when the speed or direction of wind changes very quickly, and it can be rough on airplane wings. So those are examples that we're good at. There's also some examples that we are not very good at, and those are the models of living systems. So while we are really good at mechanical systems, and our models are really good at making predictions with mechanical systems, we are definitely lacking in living systems. And in fact, about 20 years ago, the National Science Foundation was looking for people who live right here. It turns out that college students, when they go into grad school, typically you've got math students who are really good at math, or you've got biology students, or biology or life science students, but we don't have a lot of people right here in the middle. So we had students who were really good at making mathematical models. We have students that are really good at understanding living systems, but we don't have a lot of students in the middle here. So it was probably about 20 years ago when, if you were a graduate student and you were good at both of these areas, you pretty much could go to grad school for free. So I looked into this a few years ago, and a lot of these programs don't exist anymore, but we still need students here. So if you're good at math and mathematical modeling, maybe computers, and you also are good at biology and interested in both of these, there's a lot of research areas for you. So I'm going to mention, for example, too, some of these systems we have, these computer models that we're using, but they're just not very good. So, for example, let's say you have a new drug for, let's say, combating diabetes. Well, we have computer models here, but they're just not very good. For the most part, when we're testing a new drug, we have to go through these drug trials, which take a tremendous amount of time. They're extremely costly. And if we had better computer models of of living systems, we could just save a tremendous amount of time and money here. So anybody who's interested in this area, we need you. We need you to go into research in grad school and come up with some better models. But we do have models. So part 3 here is just saying there's another way you can produce data is through computer simulation. Okay, we've got a few more here. So a common way to get data about people is to ask them questions or conduct a survey. Sometimes responses are yes or no. Often respondents choose a number on a scale that represents their feelings from, say, strongly agree to strongly disagree. And this one is really popular right now, especially with online polls. So such a scale is called the Likert scale. And they are used all the time. There's some controversy with them. So we may talk about this later, but basically if you have a scale that looks like this. So maybe strongly agree is 1, strongly disagree is 5. We'll see later on that if the gap between these is not the same, then there's certain statistical methods that shouldn't be used. So some people argue that the gap between 1 and 2, the change in feeling between 1 and 2 is the same as the change in feeling between, say, 3 and 4. Others say that it's not. So we'll see. But Likert scales are used all the time. A little note about surveys, though. There are a lot of potential problems with surveys. So this first example right here, let's say it's Saturday morning. You are just waking up after a long night of doing statistics homework, of course, and there's a pounding at the door. You go to the door, you open the door up, and there's a uniformed police officer, and he says, yeah, we are conducting a survey about the use of illicit drugs. Just wondering what your thoughts are. And you would probably say something like, we are against those. It's a uniformed police officer. Okay, so let's say this police officer is conducting a survey in part of the neighborhood. So we've got, say, uniformed police officer. And then we'll say the other part of the neighborhood, the survey is being conducted by a college student who just shows up, t-shirt and a pair of shorts, and asks the exact same questions. And you can imagine they were probably going to get back to the office. The police officer is going to be, well, it seems everybody's against the use of illicit drugs in this town. And the college student may have different data. So surveys, there's just a lot of problems with surveys. You can see some of them down here. The wording is different. If you have a survey and you use the word Obamacare, and then you have the exact same survey, but instead of Obamacare, you put in Affordable Care Act, you get completely different responses. And everything matters, especially with a face-to-face survey. People tend to skew their answer a little bit to what they think the surveyor wants to hear. It's just kind of a human nature. So if the surveyor is old or young or male, female, everything matters. The way they speak, race matters, the way they're dressed, everything matters with a survey. So you just have to be really, I guess, cautious about any information you get from a survey. So when you get a chance here, just take a look through here. There's just the takeaway is be careful of information that comes from surveys. Another example, that is also you have to be a little skeptical of, is mail-in surveys, which are not done too much anymore. Since the internet has been on the scene, now we have email. You still have to be careful with these surveys also. Mail-in surveys or email tend to receive the most responses from those with strong opinions. And when surveying was sort of at its infancy in the early part of the century, there were some presidential elections that were, you can look them up. It's not even that early, like 30s and 40s. Just huge disasters where the survey responses would come in and the newspapers would print the results of a presidential election that would be wrong. This is because at the time people didn't understand the effect of biased answers. So the mail-in surveys were from people who had magazine subscriptions. So they tended to be the more wealthy people. So the data were really skewed. So any kind of survey, not that they can't be done well and give good information, but you just have to be a little careful about those. Okay, and now we're getting to the last couple here. So one of them we'll look at is an observational study. So in an observational study, observations and measurements of individuals are conducted in a way that doesn't change the variable being measured. So, suppose you want to study the effect of smokers on lung capacity in men. You compare the lung capacity of a group of smokers to the lung capacity of a group of non-smokers. So you can imagine the problem with doing an experiment here. Let's say instead of the observational study, you wanted to study the effects of smoking on lung capacity in men. So you have a whole bunch of males, you put them into two groups. You got this group here, this group here. None of them smoke. And you say, okay, what we're going to do is just have this group here just do nothing, just go about life. This group here, we're going to have you start smoking a pack of cigarettes a day. Then we're going to come back in 6 months and measure lung capacity. Okay, so you can see this is not going to work. So instead of that, we would do an observational study. Another example right here, and this is a big question over the past few years about repeated concussions. And there's been a lot of talk about it because of football. I've always been talking about boxing, but football is a newer topic. And it's trickled down to kids' sports. So it's an important question, and definitely you can't do an experiment here and sign up a bunch of volunteers to get knocked in the head ever so often and then look at results later. So instead, you would look at groups of people who maybe participate in contact sports and compare that to maybe a group of people who compete in sports that are not contact sports. So these are observational studies, but the key is you're not changing anything. You're dividing people into groups, you're noting differences amongst the individuals, but you're not imposing a change. You're not saying that this group is going to do anything different. You're keeping things as they are and measuring. Okay, so that's an observational study. So the last one here is the one that's probably the most important. And this is a popular way to produce data. This is to perform an experiment. So in an experiment, A treatment is deliberately imposed on the individuals. And you do this in order to observe a possible change in the variable being measured. Now, this treatment doesn't need to be like a drug or anything like that, although it is often in human studies. But it could be something like, okay, we're going to see the effects of lack of sleep. So we want to have a group split our people into two groups, and we're going to have one group sleep only 3 hours a night, and then the other group will sleep normally. So a treatment could be any change. It could be we're going to water this group of plants more than this other group of plants. Okay, so it doesn't have to necessarily be some sort of drug. It could be just about anything. And experiments are commonly used to determine the effects of a treatment. We need to design the experiment to rule out or control for other possible causes of the effect. So we need to be aware of these other things that could be causing changes and control for those. So we need to, there's a couple things you can do. We could make sure that everybody has that. Like when we talked about the smoking groups, you'd want to make our groups be full of smokers or full of non-smokers if we think that could be a cause. Or we want to just have randomize it so that each group should have a roughly equal proportion of smokers. So we had to be alert for that. So we want to control other causes of the effect so that we can just look at this one change and see what is happening when we make this one change on one of the groups. So when we set up our experiment, we have to be aware of the placebo effect. This occurs when a subject receives no treatment, but incorrectly believes that he or she is receiving treatment and responds favorably. And also, replication is important. The repetition of an experiment on a large group of subjects. This reduces the possibility that a measured effect occurred by chance alone. This is actually becoming a bit of a problem in research because it's been getting harder and harder to find funding for replication studies. But it's really important because that is what gives us confidence in science. It has this built-in error correcting, so that if there's a study that's published and then some other researchers repeat that study and they get the same results, that's how we get confidence. So if a study is published and nobody repeats it, if the study just came to the wrong conclusion, we wouldn't know. So replication studies are really important, and they are unfortunately getting less and less likely to happen. Okay, then we've got a block. This is something that's mentioned in the book, and I'll just tell you right now there's a homework problem that's going to give us some trouble. It's based on blocking, but it's a kind of a tricky question for, just being introduced to blocks here in this little blurb here on our handout, and the book has a little, couple of sentences about it. So problem number 11 in the homework may give us trouble, and we will most likely go over that one. So it has to do with blocking. So a block is a group of individuals sharing some common features that might affect the treatment. So often subjects are assigned to blocks based on gender. This is in human studies, especially in medicine. It is known that men and women are physiologically different and react differently to medication. So suppose we have two blocks. One block has 250 men who get a placebo and 250 men who get the treatment. The other block has 250 women who get a placebo and 250 women who get the treatment. This design ensures that each treatment condition has an equal proportion of men and women. As a result, the differences between treatment conditions cannot be attributed to gender. So you're ruling out that. So if there's something happening or not happening, it won't be because of gender. So this randomized block design removes gender as a potential source of variability and as a potential confounding variable. So the one I was mentioned in the book is dealing with some sort of fertilizer. So there's an example of that in the homework of blocking. And with experiments, although there's great ways to get information, there are some potential problems. One of those problems is generalizing results. So anti-cancer drugs that work well on lab mice, they don't necessarily work well on people. Sometimes they're even poisonous to people. So they actually hurt people somehow. One that works on adults doesn't necessarily work well on children. So we don't want to generalize. And the study sponsor, if a company is paying you to test their new drug, you may be more likely to dismiss a rare negative finding. And this is just something to be aware of. So as an example, let's say you are running a lab and you receive some funding from a company that wants to test out their new fertilizer product. And you know they're hoping for good results. So you set up your testing, and let's say there's a particular plant that's not doing well and it has the new fertilizer, and it, there's a temptation to say, I don't really think I watered that one properly. I'm not going to count that one. Just something to be careful about. We have to always be completely honest when we're conducting these experiments. So here's an example of a medical experiment. So let's say you have patients that are divided into two groups by a random process. And you may even be asked to be involved in one of these experiments. So I remember when my son was in the hospital after he was born. I don't even remember what this was for, but we were asked to participate in a study. It may have even been allergies or something like that. And so the hospital had received funding and was involved in a study, as many hospitals are, especially like for Alzheimer's and things like that. And I think that study ended up not working because I know it didn't end up running. So I know he was not involved in it. But basically, in situations like this, what you do is you take all the patients you have and you divide them into two groups by a random process. So what you'll have is you have this group called the treatment group. And they're going to receive, this group will receive the treatment, whatever that is. So in human studies, a lot of times this will be some sort of medicine. So the treatment group receives the treatment. Then you have this control group. And they're going to receive a placebo. So the thing is, it's going to look exactly the same. So if they're getting some pill, this pill will be exactly the same, but it will not have the active ingredient. So that's important, as we'll see. So it looks exactly the same. So the key is that these people don't know what group they're in. So you have a whole bunch of patients. They're all going to participate in this study. You divide them randomly. So you have these two groups. This group is going to get, say, some pill. This group is also going to get a pill, but this will not have the active ingredient, and this group doesn't know that. So you don't know what group you're in. And then the experiment is run. So maybe this is done for a month. Maybe every day for a month you take this pill, and then you come back to the hospital and do the results. So an example, maybe these are groups of patients who have migraine headaches, let's say. So maybe it's a migraine headache group. So they'd have to have something in common, like maybe all of these patients get, let's say, 5 or more migraines every month, something like that. So you divide them randomly into these two groups, and then after everybody takes their pills for a month, for instance, and you go back, you talk to the researcher, and you look at how many migraines you've had. Okay, so then to compile the data after the treatment cycle, the patients are evaluated by the doctor. And here's something that is important too. The doctor or the researcher does not know which subjects are receiving treatment. So it makes it a blind study when the participants don't know what group they're in. It makes it a double-blind study when the person who evaluates also does not know what group these people are in. And at this point, you have what's called a double-blind study, which is what you want to have. This is a double-blind study. Double-blind meaning these people don't know what group they're in, and also this person who evaluates at the end also doesn't know what group they're in. So then you compare and you see, does this group here, did they do better than this group? So remember, this is a placebo. The placebo effect is in here. So even if the pill doesn't work, this group should improve from the placebo effect. So the way these are done is you have to have this comparison, because typically both groups will improve, if nothing else, from the placebo effect. So this group has to do much better than this group. And we measure that phrase much better using statistics, which we'll find out later how to do that. But the key is you need these two groups. So the way bad science is done is you just have your group. You don't compare it. So you just have your group and you give everybody your new drug, and surprise, surprise, everybody, there's an improvement, and that's what you're measuring is the placebo effect. So you need two groups. Most of the time, both will improve. The question is, did this group improve a lot more than this group? Right? Was there a measurable difference here? And we'll talk about statistical significance later on, but that's what we're looking for. So this is a double-blind study. It's really important. So maybe mention one more thing here. These double-blind studies are important. Because they eliminate bias. There's a lot of bias that will be eliminated if you have a double-blind study. So let's see, the condition of the patients in the treatment group is compared to the condition of the patients in the control group. This is what we already talked about. The important question is, did the treatment group do much better? Which means, were the results statistically significant? So did the treatment group do much better than the placebo group? Because remember, the placebo group should show some improvement from the placebo effect. The treatment group has to do much better than that, and we'll talk more about this when we have some tools to work with. And essentially we're saying that the results were statistically significant, which means it's unlikely to have occurred by chance. Right? Because if you just took two groups and they both have the same thing, let's say they both take the medicine, well, just from chance alone, one of them would probably do better than the other one, right? So it's not good enough just to say, the treatment group did better. They have to do much better, like better to the point where you think it wasn't just chance alone. Okay, so anyway, that should take us through section 1.3. As I mentioned, it's a really important section, but we don't get into good details. But some of you who are super lucky, who may be major or minor in statistics, or will go into science and have to do some research, you'll get into a lot of details about this when you take your design of experiments class. So try the homework and let me know if you have any questions.